I'm Bertrand Leroy, and today I'm here with Phillip Carter. Hi, Philip.
Hey, how's it going?
Good, how are you?
I'm quite well.
I just asked you that. And today we're going to talk about F Sharp.
Yes, we are. F Sharp is a wonderful, wonderful .NET language that we have that I happen to work on. And there's some really amazing things that it can do, and hopefully we can kind of talk a little bit about that and show off some of those capabilities, some of the sexy features that it has, and hopefully interest some people in picking it up.
Cool. And you've been the PM for F Sharp for how long?
Officially? A couple months. Unofficially, a couple months before that.
Yeah.
Most of this year, I'd say.
Okay.
Yeah.
Before we talk about F Sharp, we have a couple of announcements. I'll switch to the screen here. So first, during the demo, during this show, you can ask questions on Gitter. So can you switch to Gitter?
Yes.
We're gonna answer questions on the .NET/home channel of Gitter. So please feel free to ask questions at any time. So the announcements we have been relayed on the blog as well. The first one is that the preview for Visual Studio VS 15, which is not VS 2015, confusingly enough. So the preview is out if you want to switch to that tab.
Yes. That tab.
I'm making you do all the work here.
.NET? No.
But you had it open 5 minutes ago.
Oh, no, I had it open in Parallels, but not on the Mac. I think I may have, did I close it in Parallels? No, yeah, I did, okay. But hey, here we are. The Visual Studio 15 preview for blog post.
So the main attraction here in that new preview of Visual Studio is the setup experience, which is very different. So I encourage all of you to try it and provide us some feedback.
Yes, this is so. Having been involved in some of this, and making sure that when you select something where F Sharp might supposed to be in there, then making sure that F Sharp shows up and things like that. Definitely encourage you to try this out. Try to find unique ways to break it if you can. Try to go through your daily workflow through this installer and basically think to yourself, okay, I selected this, I expected these things. Did I get these things or did I not get these things? And then if you didn't, please leave feedback. And if you did, also leave feedback if you're really happy with it. We're working really hard on trying to get this figured out really well. So yes, I encourage as many people as possible to download and play with this.
Yep. Another announcement is something that actually ships with that same preview is C# 7. So Matt Storgerson wrote a very nice blog post on the .NET blog, if you can navigate to that.
Yep.
Sorry. So Matt is going through all the new features that appear in C# 7, and check it out. It's very nice, very interesting.
It's pretty cool. My personal favorite is pattern matching, coming from F Sharp, which has this feature. It's interesting to see how it's panning out in C# in a way that is, it's nice because it's not trying to just wholesale copy F Sharp and say, oh, well, here you go. You have this little mini language in C# that's totally different from the rest of your code. They spent a lot of time looking at, what are the key benefits that they can get out to people right away in a way that makes sense for C#. And it turns out type patterns, constant patterns, var patterns, patterns for tuples, all this sort of stuff are the things that kind of make sense holistically with the language today, and that give you immediate value without them, inserting something into the language that may potentially feel awkward compared to the rest of C#. And that's something that they have to be awfully careful about, because once you add a language feature, it stays in the language forever. There's no getting rid of it.
You don't deprecate language features.
Yes. If you deprecate a single language feature, all of a sudden millions of people's code will just break, and trillions of lines of code will just fail. There's just So it's very exciting to see how that's all panning out.
Excellent. Why don't we switch to F# then?
Yeah. Let's talk about F#. So F#, we like to call it a functional first multi-paradigm programming language. So that's
Hold on. Say that again.
A functional first multi-paradigm programming language, which is a whole lot of words that actually is really, really simple.
Okay.
Every single programming language that we create.
Let's break it down then.
So every single programming language that we create for the .NET framework and for now .NET Core is a multi-paradigm programming language, meaning there are different programming paradigms there's imperative programming, object-oriented programming. That's by definition, if you support these sorts of things, you are a multi-paradigm language. So C# is one. And so C#, as most people probably know, also has these functional constructs through link. And async, you could argue, is also a bit functional in nature. And so functional constructs, meaning from the functional programming paradigm. But F# takes a different view, which is instead of saying, we have a few of these little functional programming features that kind of surface through the language, we are functional first in that the functional programming paradigm is kind of the default way that you go and do stuff with F#. The path that you are led down when you are writing code is one in which using functional programming constructs make the most sense. So that means a couple of different things. First of all, and arguably the most important, immutability by default. So you don't define variables, or at least they're not called variables in the same way that they're called variables in C#. You use primarily what are known as bindings. So you bind a name to a value. And that value might also be a function, or it might be the result of a function. But then once something is bound, it's set in stone. You can't just change it in place. It'll be a compile time error if you do that. Now you can get around that with being explicitly mutable, which is what's known as using the mutable keyword. But that's you saying, I know that I need to update this in place for some reason. Oftentimes it's performance purposes, like you just need to eke out the most possible performance that you can get. But then it's an opt-in thing instead of things being mutable by default. And so that's very important for things like concurrency. So if you're doing any kind of multi-threading, if things are mutable by default, then there are so many things that you have to watch out for. You got to be careful with almost every single line of code that you write. Whereas in a functional language such as F#, where things are immutable by default, you don't really worry about that as much because you say, my data is immutable. Like how I'm representing that data is
so you
immutable.
Don't need to lock it. It's just going to remain what it is.
It can eliminate a whole class of problems that are normally a concern with languages that are mutable by default. And this gets even more important in distributed scenarios where you're thinking about, this routine is running on this node, and then this one's running on this node. This one's maybe running on this cluster versus this cluster. Maybe this one's running in a different data center. There's just all these different levels at which things could be going on. And if things are mutable by default, then all of a sudden you could have written some code that just, there's this strange conditional branch that it managed to go through and it changed something on you in one place, but it didn't change it everywhere else. And all of a sudden you have this inconsistency that is really, really hard to debug. Those are the kinds of things that take people weeks to figure out what actually went wrong. So that's one of the
there are immutable structures that you can use in C#, but they are not the default. You have to.
Exactly. So that is worth bringing up. In C# and Visual Basic, you can use the even in F# you can. You can use the immutable collections library, which kind of buys you some of that. But it's still, because it's not at the language level, you typically have to watch out for those sort of things in different areas. There are a couple of other benefits. So one of the key tenets of functional programming is that you think about things in terms of functions, inputs and outputs. You have a function that takes in some inputs, it does some work, and it generates an output, and there's no side effect. and then you just work with the outputs of other functions. And maybe you compose functions. So the output of one function is the input to another function, and you can set up these pipelines of functionality. And so that lends itself to a style of programming that's really, really great for a wide number of things, but typically the most applicable scenario is sort of the middle layer of your application. So you have your user interface that accepts some input data. Maybe you have to interact with some framework that is mutable or object-oriented, and it's kind of awkward to use functional programming constructs around that. And so then you might say, okay, well, I'm going to be imperative. I'm going to be object-oriented in this layer, but then I'm going to call into some stuff. And then like 80% of my code base is just going to be these functional data pipelines, because oftentimes that's the case where you just say, okay, I collected the information. I need to go send it somewhere and perform some work. Maybe it retrieves some information from a database. Maybe it hits another web service or whatever, and does some sort of meaningful work and provides me a result that I can then interpret in any way that I need to. And so that typically like large area of an application, you can oftentimes model the majority of those code paths as functions themselves. And so those functions can just be a large function that is composed of a pipeline of smaller functions that maybe they have some sort of special error handling, and there are a lot of patterns and practices for that style of programming.
So in this style of programming, how do you avoid doing a lot of copying around? Because if everything is immutable and you take an input, give an output, aren't you going to copy a lot of the input into whatever structure you give in the output? Do you see what I'm getting at?
So you mean like using like structures more often rather than or like pass by.
Yeah, aren't you going to do more allocations in some cases than you should?
Yeah. So sometimes, well, I shouldn't say sometimes. The majority of time, you will have effectively marginally less performance than if you were to use an imperative language, just because there are a couple of things like structural equality. By default for what are known as F# record types, which are typically these data holder types that you put things into. And so there is a little bit of overhead in that. But typically it's really more a question of what's the order of magnitude that really matters for what you're doing. Like if you are dealing with, I need to handle 5 million requests per second on this sort of thing, and I'm dealing with bytes, then it may not necessarily be the best choice to use those functional constructs in F# because you will get that overhead. But if you're just dealing where the thing that really matters is something crashes, like a node goes down or something like that, and now the entire service is totally gone. Or you're doing some sort of really heavy-duty locking with imperative code because everything is mutable by default, and then the overhead from that all of a sudden overcomes the overhead from just having immutable structures by default. There are a couple of things in overhead when you're dealing with some of the data structures, like immutable dictionaries, for example. They're typically implemented as AVL trees in the background, or some sort of tree-like structure where you no longer get constant time access. It has to do a sort of search into it, and then there's kind of like this in-place replacement of nodes that goes on when you're adding and removing things, so you're never really deleting information. You're just kind of presenting the underlying data structure in a new way to people.
And you'll rewrap a lot of existing objects.
But typically, in fact, I would say for the vast majority of applications out there, that kind of overhead is the sort of stuff that is just kind of like lost in the noise. And so what people typically find is when they use immutability, and I shouldn't just say F#, but just immutability by default, is that they do get overall sort of wall clock time performance gains, because they're not, some of the problems that they may have incurred, like some sort of crash or some sort of thread issue that they were having, was causing a large delay in something that was just part of the normal application behavior that just disappears. That's sort of how that happens. And so there are a couple other things. So you model things as functions, things are immutable, and then the other key thing with F# and a lot of other functional programming languages out there is the type system, and specifically using type inference to get what we call automatic generalization. So this is something that I'll actually just show off right now because it's kind of cool. So say you wanted to define a function that just squared a value. So I'll just go let square x equal x times x. This is just one line of code, but I have defined a function right here. If I hover over this right here, it might be a little difficult to see because the tooltip doesn't get larger, but it says val square colon x colon int arrow int. So the compiler was able to say, oh, well, I know that x is an int, and multiplication is defined on integers. Now, if I were to use this in a different way, if I were to go, I'll go printfn, we'll just say it's hello, and we'll go %f for a float. And then I called square 3.0. All of a sudden now it's changed. And I don't have, it said int before, but now if I hover, it says x is a float because the way that I'm using it, I'm passing in 3.0 and then I'm doing a format string where there's this %f, which happens to be the format string for floats. And so it says, oh, well, square is now a thing that operates on floats. And if I try to use it again as an int, so if I'll go square 2, I'll just ignore the output of that really quickly. This will actually be a compile time error because it says the expression was expected to have type float, but here has type int. And so this is because we've effectively said, hey, we've determined that this is a float, but now you're trying to use it in these two different ways, and we don't understand what's going on here. This is, I don't want to say a limitation of the language, this sort of function overloading thing, but this is a huge issue with type inference language overall, which is, type inferred languages, which is the ability to have function overloading in the face of global type inference. There was a pretty fun bug in the Swift language not too long ago where you could just do some basic arithmetic for integers and then say that the result was a double and you would get exponential compile time because the type checker would have to go in and try to solve what's known as an n-by-n Cartesian product of all possible inputs and outputs, and it just exploded. They're fixing bugs like that all the time, but I mean these are the sorts of things that F# has chosen to effectively avoid by saying, okay, well, we'll give you type inference, but if you're going to try to do this function overloading thing, you need to be explicit about what you're actually doing here. However, this is just kind of the very, very beginning of what is awesome about F#. So if I could go let's actually just get rid of this line here so it's back to being able to generalize here. Sorry, I'll go let is odd, x is equal to, we'll go x mod 2 is not equal to 0. So that all this is doing is just checking if something is odd. And then we can say, okay, now we have these two functions. It's saying that they're both ints. This is all fine and dandy. Now what if I wanted to generate a sequence of these things and then sort of build up a little functional pipeline here? A great way to do this is using the pipeline operator, which I'll show off now. I'll go get, what should I name this? Get squares of odds. We'll go items. We'll go items. seq dot filter, sorry. We'll go seq dot filter is odd. So I'm just going to type this out, and I'm going to explain what I'm actually doing here. And then I'll do another pipe here, and I'll go seq dot map square. So hang on here. I'm just going to make this guy happy. That's because I misspelled is odd. There we go. Okay.
Okay, so you have this pipe operator that is taking the output of one thing and putting it as the input of the next.
Exactly. Right? So kind of walking through what's going on here, I've defined a new function called get square of odds. It takes in items. So items, it now knows, is an seq of type int. seq is actually just a type alias for IEnumerable. So it has the exact same characteristics. It's just
so it stands for sequence.
Yeah, exactly. So a sequence. And so I'm taking items, and I'm piping it to the input of the seq.filter function. Now the seq.filter function is a function that takes in a predicate function, much like the where clause in in C# and Visual
So
Basic.
your predicate here is odd.
Yeah, so one thing, just to stop right here, I'm passing in a direct function here. Notice that I didn't have to, construct some sort of thing here where I go fun x such that x, like I didn't have to construct a lambda which then allocates a delegate or anything like that. I could just pass in a regular F# function because functions are what are known as first class values in F#. So you can pass them as inputs to other functions and they can be outputs as other functions. And that's actually really awesome because I don't need to sort of have this thing that's a function but is not really a function compared to the other stuff. So like a lambda expression is not a method in C#. But this is just a regular old function, which is kind of cool. But something that you might notice, which is a little odd, is seq.filter. It takes in the predicate, but then it also takes in a source sequence. Where's that source sequence? It's not defined here. I'm just passing in this function. This is because this guy right here, or rather this right here, this pipe operator, is what's effectively taking the thing that's on one end and then putting it over to the very end, or shoving it over to the end there. It's able to take advantage of this through what's known as partial application, which is another functional programming construct that effectively allows you to partially apply functions as you need them. So in this case, seq.filter takes two inputs. You can partially apply parameters to that function as you need it.
It's currying.
Yeah.
Okay.
Yeah. So it's all backed by currying, and so there are a lot of clever ways that you can take advantage of that.
It generates a new function that has some parameters already passed in, but still has the placeholders for the remaining ones.
Absolutely.
Yeah.
Yeah, and so then you can compose those really easily, and that allows you to do some really succinct code, which is fantastic. But it also allows you to do things like you can use partial application for caching strategies if you need to. So you can cache the result of something with the first parameter and then pass in that function that's partially applied. So there are a lot of ways that you can get clever with it.
Yeah.
But the most basic usage of that is kind of more of a in the background usage by being able to pipe things together. So then I'm taking the output of seq.filter with the isodd function passed in, and then piping that output into the seq.map function. And seq.map is the same as select in C# and VB. And then I'm mapping the square function over the inputs there. So to actually run this, I'm going to do what's known as sending this over to the F# interactive window. So you may have noticed this thing on the right-hand side, this F# interactive type help, pound help, semicolon.
So when you do F#, typically you keep the console open?
Well, a lot of people have different development styles. My personal style is when I'm building something, I will keep it open for interactive stuff as I'm building out an initial solution because I just want to play with it and see what's actually going on here. I'm going to hit Alt-Enter. You can also right-click Send to Interactive, but I'm hitting Alt-Enter here. And so you notice a few things showed up in here. This thing called val square, and it's got this notation where x:int and then arrow to int. This is saying that square is a function that takes x, a thing called x, which happens to be an int, as its input, and then produces another int as its output. So this is just like type definitions. Isodd takes in an int, produces a bool that we can then test on, and get squares of odds takes in items, which are seq event, and then produces another seq event. So in this case, it's going to be a different sequence. So if I could go get squares of odds, and then we'll just do 1, 10, from 1 to 10. So I'm using some list syntax. I'm basically just generating a list here. So this generates an F# list starting with an item called 1, and an item of value 1, and then ends with an item of value 10, and it sort of fills in the rest. So what I've generated here is this new sequence, and it's 1, 9, 25, 49. It does a ... to elide output because you could have a whole ton of output and it doesn't want to explode your screen space when you do that. So kind of walking through what I did here, I generated an F# list, which is, it's actually implemented as a singly linked list, which is kind of interesting. There's some historical reasons for that. Generated an item from 1 to 10, and then I sent that in to get squares of odds. You'll notice that effectively just went straight through the filter function. It filtered out all the even ones, so that all I had were the odd ones. And then then those got squared. So 3 got squared into 9, 5 got squared into 25, 7 to 49, so on. So this is kind of an interesting style of programming here. This is interactive programming, or sometimes it's known as REPO-driven development, where you're prototyping out an initial solution to something and you want to get immediate feedback on what things are. So you can just select functions as you need them and then send them over to the F# interactive window, and then just start calling them. I'll go from 5 to 13 or 13. So 25, 49, 81, 121, so on. So I can just sort of play with different outputs and sort of see what it looks like. It's a really fast sort of feedback loop in terms of seeing what's going on there, as opposed to needing to set a breakpoint, wherever I could set a breakpoint. Set a breakpoint, try to run it, see what it looks like. Typically that's a lot slower, and it's certainly a lot slower than running your application and then seeing what it all looks like. So this is sort of a lightweight way to sort of do this thing. And then typically what happens is after you've built out what you think is a pretty solid initial solution, you'll go and say, okay, well, I'm going to start writing unit tests so that I can really solidify what I'm trying to do here. And so then you can be more resilient to change when you need to go and add new features and so on. But I want to show off why. So like this, some people might find this somewhat useful, but I think a lot of people are saying, okay, you've defined a square function, you defined an is-odd function, I can do this in C#, like no problem. What's so special about F# in this case? Let's be a little bit more interesting here. So I'm going to go open system. So open is the same as using a namespace in C#. So I'm opening the system library. And I'm going to define a new module. So I'm going to go, we'll call it try parsing. So a module is effectively a holder, like a container for functions and values and types and things like that. It's sort of an organizational construct for F# code. So what I'm going to do...
So the closest in C# would be a namespace, maybe?
It's analogous to namespace, although we also do have namespaces in F#. Typically what you'll do is modules are for organizing code, and namespaces are for organizing what you expose when you want somebody to call into your code. So if I define a class library in F#, and then I want to invoke something from it in C#, then sort of the name that using blah in C# will be defined as the namespace name. So I'm going to do something kind of fun here. So I'll do let private. This is so that if you try to open try parsing, you won't be able to see the function that I'm using. This is just some accessibility modifiers. We'll go try parse function. We'll just try parse func. And I'll just pass in something called f. And f is just a function. So I'll go f. And I'm using this other special little operator. So this thing right here is a little bit of a riff on this pipe operator. This is what's known as a function composition operator. So this is a way for you to compose two functions where you know that the input and output types are sort of compatible with these two functions, and so you don't need to explicitly pass in the parameters of the input types. I will sort of show what that really means here. Actually, I'm just going to put this on one line here. Okay, so I'm using what's known as the function keyword, which is a shorthand for pattern matching in F#. So I'm going to pattern match, and I'm going to say, in the case where something is true and there's a value, so this is now a tuple that I've just defined on the fly here, I'm going to want to generate what is known as a sum of the value. So this is the use of the optional type. So I'm throwing a lot of different things at you right now, but just bear with me here.
That's a lot of concepts here.
This is a lot of concepts that need
But you will break it down.
I'm absolutely going to break it down. The reason why I'm doing this is because they all interact with one another in a way that kind of forms this cohesive whole where you go, oh, I see.
Okay.
So there's the case where there's a true, where effectively this is saying of the try parse function that was passed in, it succeeded, and there was a value that was generated. I'm going to generate what's known as a sum of the value, or rather generate an optional of the value, where an optional type is a way of saying there's either something or there's nothing, but then at compile time you're forced to account for those two cases.
All right, so this is because that's the difference with C#, right? In C# we have null, unfortunately, some would say. Here, you don't really have null. It's that you can have optional types.
Yeah, and
which is
it's
not a space concept of monads or whatever. You don't have to understand monads to understand that. It's just that it's the same type, but now it can have null.
Yeah, well, so basically, in C# all the time things are implicitly null, and you're like, oh well, there's really that.
And you have to account for it everywhere.
Yeah. And how many times have you forgotten to account for it?
Don't ask me.
Countless, yeah.
And so $1 mistake.
It's a huge problem out there. And so in F#, well, this is really kind of a solved problem that F# is certainly not unique to this.
Yes, absolutely.
Which is saying we can take an optional type where we represent in sort of a type-safe way the fact that there's either something or nothing, and then we can force at the call site for you to account for that fact. So you call a function, it returns an optional. You have to account for the fact that there could be something or there could be nothing. Failing to do that is a compile time error. And so you don't get a runtime, oh, there was nothing here going on, which is quite powerful.
Okay, so sum of value is just saying you return that value or under some kind of wrapper that could be null.
Yeah.
Okay.
So what this is going on here is there's
a value or nothing.
So there's actually no null involved here. But then
so in this case, you will always have a value, but this will make sense when we add the other patterns.
Yeah.
Right?
And so I've actually done that right now. So you notice I've defined two cases here. So there's a pattern where something is true and there's a value. So I want to construct an optional that contains that value inside of it. Then there's the case where it's false, which indicates that this function that gets invoked could not parse what I was trying to parse. And so in that case, I don't care if there was a value generated or not because it failed, right? I'm not going to use anything that failed a parsing function.
So the underscore here is saying, I don't care.
Yes, this is saying there might be something, there might not be something. It doesn't really matter to me because in this case, I'm constructing a none, which is the other case of the optional. So this is a way of saying there is nothing here. However, it's a type-safe way of saying that.
So for people who just read the C#7 post, is that in there? No, it's not.
No. What I'm doing right now, you won't be able to do in C#7 for a variety of reasons. So what I've generated here is this function, this try-parse-func. It's got quite an interesting type signature here. Let me send that over to the interactive. Oh, boy. Okay, I'm just going to send this over to the interactive window. Okay, so I'm not going to try to execute this in the interactive window right now, but I just want to show what the type signature looks like. So it's kind of interesting here, where there's f, which is itself a function that takes in this little apostrophe a. So that's the way of representing what are known as runtime generics in F#. So the standard generic type, which would be T in C#. F# actually has sort of two forms of generics. You can have the generics that are there at runtime, or you can have statically resolved generics. Those are known as statically resolved type parameters. So I'm not using those in this case. I'm just using the type A. And so a type A, this is a function that when given a type A generates a tuple of type bool and type B. B indicates the type of value that was parsed. So in this case, if I'm attempting to try parse a datetime offset, which I'm going to do, it takes in a string, and then it generates a datetime offset. So this type A, in that case, would correspond to the string type, and this type B would correspond to the datetime offset type. And then this bool is indicating whether or not it worked. So you notice, so in C# you have the try parse, you have the out parameters, so you gotta check if it worked, and then there's an out parameter, and if it worked, then the out parameter had something assigned to it. If it didn't work, then nothing was assigned. we're able to actually implicitly convert that into a tuple here for F# consumers. So they don't have to worry about this weird notion of having to deal with out parameters. So getting back to this signature, we have that function as the input. And then this is a function that takes in a function, and then it generates an optional. Or, well, sorry, it generates a new function. Sorry, I should say. It generates a new function that takes in that type A, so in this case the string, and generates an optional of type B, which in this case would be an optional of type datetime offset. And I will show that to you by saying...
So what you've done here is prepare the signature of your actual parsing functions?
Mm-hmm.
Okay.
So what I'm doing here is, so I'm actually going to call it. I'm going to go let try parse func. So let try parse datetime offset is equal to try parse func. And I'm going to pass in datetime offset dot try parse. So I've passed in the datetime offset dot try parse function into the try parse func function. The try parse func function generated a new function which takes in this string type. So you'll notice that over here, this is all generic. This is given a type A, generate a tuple with type bool and type B, and then it generates a new function which is supposed to take in a type A and then generates a type B option. Now we're actually kind of getting a bit more concrete because...
So you're taking the stock .NET try parse function for datetime offsets and you're F#ifying it?
Mm-hmm. I'm F#ifying it for a very good reason here. So notice that now I have this separate signature here. So right below it, this try parse datetime offset function is a function that takes in a string and generates a system.datetime offset option. So this is this automatic generalization just right in front of you. So this try parse func is this automatically generalized thing. I didn't have to list any sort of type signatures. I was just using things, and the compiler was saying, well, this is what the signature has to be. And then I generated a new function from that helper function. And then I can now use this new function in a really cool way.
Yeah, and now it has a signature that really makes sense. I don't have to write this with an if.
So let's do two things here. So we'll go print fn. Let's say in this case, actually, I'm going to do one more thing here. So I'll go let do try parse date time offset. Takes in a string s. All it's going to do is match on s. Or no, sorry. So it's going to go, it's going to compute the results. So it's going to go try parse date time offset s. So I've defined an inner function inside of this function that generates a result, which is an optional. So I'm going to pattern match on that optional, and this is where it all pays off. So I'm going to go match result with some DTO. So notice that I cannot get this to compile until I pattern match on everything. There's this little warning message right here that says incomplete pattern matches on this expression. For example, the value none may indicate a case not covered by the patterns. This is just something that's thrown at my face right now. I need to account for both cases the instant that I'm trying to use this result. This is a huge payoff here. Because I can't implicitly forget to account for it and then have the compiler not yell at me for that. So I'm going to now print something. I'm going to say it worked. Let's print a little string. And I'll go DTO. So that's the datetime offset. And notice that it's this. I have IntelliSense because it's this datetime offset function. I'll just go .toString. And so I'm just printing the toString of it. Notice this is something that I find kind of cool. This is type-safe formatted printing. So I'm saying that I'm printing a string here. If I were to try to pass anything here that was not .toString, like if I just passed DTO, it'd be a compile time error because it said, oh, but in this format, you said it was a string. So that's also kind of handy. And now in the none case, I'm just going to say that it didn't work. Okay, So now this is a new function that I've defined. It's kind of awfully specific here. Do try parse datetime offset. You could probably generalize this to really do whatever try parse thing you're trying to do here, which in this case you could make really easily. Just you could say try parse int equals try parse func of int 32 dot try parse or something like that. You could define all these different try parse functions as just one-liners and then just use them whenever you need to, and you get this type safe having to account for the fact that it could have worked or it could not have worked at any point in time. But so back to this try parse datetime offset function. I'm now going to use it. So I'm just going to call it do try parse datetime offset. And let's pass in today's date. That'll probably work. 25/2016. And then I'll just call that again with some bogus stuff. Hey there, Bertrand. That's obviously not going to parse into a datetime offset. So let's, okay. Oh, right, that's what I want to start without debugging. There we go. Okay, so I have my computer in German mode. I was testing some localization, but bear with me here. This is the important part. So in the first case, I passed in 8/25/2016, and it was able to parse. But the key thing here is that I had to account for the case where it worked and the case where it didn't work. I couldn't just say, oh, just give me the result, because that would have not been able to actually generate something meaningful for me. So this is sort of demonstrating a way that you can use F# to your advantage to do things like parsing, which are kind of these errors where it's very, very common to not account for all the cases where something could have happened or specifically where it could have gone wrong. And this sort of lifts that concern, I guess I'll say it lifts that concern into compile time rather than being a runtime concern, which means less debugging on your part. And less debugging is always a good thing. I would argue that most people would love to debug their code a lot less and have to deal with more compile time errors and then not have to worry about things like null, because there's no null involved here at all. I just construct these F# types that all just, and now I have to pattern match to account for it, and now I have this sort of guaranteed correctness, this sort of structural guaranteed correctness, which is kind of a really big theme of F# code. So I want to show something a bit more interesting here.
Before you do that, can I ask you to go back to that greater than operator, the composition operator here? And maybe now that we've seen the code and we've seen how it works, maybe try to explain exactly what it's doing. Because that's the part of the code that I still find a little it's a little tricky. So let's kind of build up. So I feel like this pipe operator is fairly easy to understand. It just says, oh yeah, the left-hand side, just shove it into the input for whatever's on the right-hand side. Yeah, it's a familiar this one is a familiar concept, I guess, for pretty much everyone.
Yeah, it's like Unix pipes, just building up a little pipeline here. But in this particular case, if I were to pass in, S in the string S, and say like, okay, now explicitly I have to call f of S, and I have to pattern match on it.
This makes it work on any function. This is what makes it so easy to create a new try parse int.
Yes.
Using the same logic.
Yes. So what I'm doing here is I'm saying that all of the logic here, in terms of defining what needs to get parsed. First of all, so what's the function that's parsing, and kind of what its inputs and outputs are, and what I do based on those inputs and outputs. That's generic. Like that's not, the notion of a try parse in .NET.
So is it just about taking a function as a parameter?
Yeah.
Okay.
Yeah. So I mean, if you think about it, the notion of a try parse in .NET is not unique to datetime offsets. It's not unique to datetimes or ints or doubles or anything like that. It's this sort of general pattern of, I take in some input, I attempt to parse it, and I say whether or not it parsed, and I might give you the value back.
Generics give you a tiny glimpse of that generic implementation that applies to many types, but this takes it to the next 3 or 4 levels.
This is a whole other level. And so the way that you sort of play with that code, because you're not dealing with explicit input types, is instead, so the analog to this pipe when you have the explicit type and you're shoving it into the input of another thing, and then the output of that is the input to another thing. This is analogous to that, except for strictly dealing with functions. So I like to think about it in terms of defining an alias for a functional pipeline. So this is really a functional pipeline here. I have an f function, which in this case happens to be a triparse, and that triparse generates an output that then has to go into this new function that interprets that output and does something meaningful. In this case, it generates an optional. And so that itself is kind of this pipeline. I've just defined it. And so now I need to have a name for it, because it would be really silly if I were to just copy and paste this code everywhere I was going to use it. So I need to give it a name, and I gave it a triparse func name. Triparse func, all it is just an alias over these two functions that happen to be composed to one another. It's just I'm not explicitly passing in the input parameter and then saying, oh, that's the input to this first thing, and then the output of whatever that is the input to that second thing. And the reason why for that, the reason to do that is because the fact that I could have defined a function that took in that explicit input type, like the fact that there's an explicit input type is actually not really all that meaningful, right? It doesn't do any work. All it does is just go into a function. And so I am a function that it goes into, and all I'm doing is putting it into another function. And so this is a way of saying, hey, well, that's actually not really meaningful information for you to look at. So, why not, not have to worry about it. So I will say that this composition thing is not used as often as the piping. Piping is used all over the place in F# code. This is typically used more in scenarios where you're defining some reusable code that you're going to use throughout the rest of your code base, or maybe you're a library developer and you want to have all these different ways to sort of access functionality in sort of generic ways.
Would it be kind of accurate to say that the pipe operator is more about composing data, and this other one about and then this composition operator about composing functions?
Yeah, that's a very good way of thinking about it.
Okay.
So these are sort of two really powerful tools in your toolbox here for code reuse and just sort of brevity in code. So you have the brevity in code. Personally, I really like it because it's less code for me to have to look at 4 months in advance when I've forgotten all the code that I've written, and all of a sudden I now have to go reread everything, and I go, what was going on here? What was I even thinking? I can't even understand. So something that you'll notice here with F#, like there's no curly braces, there's no, the parentheses are sort of like really as you need them. I guess you could argue that's a bit more of a personal taste sort of thing, but it is less of a cognitive load. There's less stuff on the screen in terms of what it's trying to get across that it's doing compared to other languages out there.
But space is significant here.
White space is significant. That's sort of the way that you deal with that. So, well, if you're one of those people who really, really hates white space significant, then I suppose F# would not be for you. But if you love playing with other programming languages and trying this sort of stuff out, this will totally be your jam.
Well, I like Python, so.
Python's awesome. I like it a lot. Python's taking a lot of new features from some of these functional languages, but that's a whole other episode to talk about. But I want to do something a bit more.
Yeah, but it wouldn't be an episode of Fun.net.
No, Python.net. No, but so I'm going to do something here. So you notice I have these 3 projects in my solution. I had this console demo where it was just this dumb little console app. I'm going to set this thing that I call DemoBot as my startup project. And let's go over here. We'll go bot. Open up the bot framework in German. So I've got a couple things defined here that hopefully it blows your mind. I'm going to be opening up these 3 files here, and F# Interactive chose to go off the rails. So a whole bunch of new code here. Let's talk about this. So this, at the very top, you'll notice it says script.fsx. In the solution, I have this file called weather.fs, which is just an F# file. I have this other file called script.fsx, which is an F# scripting file. So F# scripting, so this thing that I was doing where I was sending stuff to the interactive, this is sort of like your true way to really script out something and sort of see what's going on. And sort of the scripting mode is this new well, I shouldn't say new, but this other way that you can do stuff in F#. I've got some code commented out here, but I'm going to really do something special here. So the first thing that I have is, in my references, you'll notice this thing called f#.data. Now, f#.data is a NuGet package. This is a NuGet package that contains a whole bunch of data manipulation stuff written by some of the most awesome members of our community, which, by the way, we have an incredible open source community with F#. Super, super intelligent people building fantastic things. And one of the things that they built here is this f#.data library that contains a whole bunch of different stuff for data manipulation. If you are in the realm of data science, this will be of high interest to you. So what I'm doing is this first thing, this pound load weather.fs, this is just sort of a way of saying that I'm associating whatever code that might exist in here that I want to import. In this case, modules, namespaces, that sort of stuff. I can then do that. And then this pound R is a way of saying, referencing the NuGet package that's sitting on disk. So in this case, the tooling is able to actually figure out where this is, so I didn't have to actually hand type this. But it's just one directory up. One directory back, packages, f#.data 2.3.2, blah, blah, blah. And it's got the DLL there that came in the NuGet package. So I'm just going to first reset my interactive session in the interactive window. And now I'm going to send over a few of these things. Is everything all right? So I'm going to send over a few things. So you notice here, this said loading a whole bunch of stuff, referenced f#.data 2.2.3.4. So what's going on here is it was able to reference all the types in the, all the public types in the f#.data package, so I can start using them. So I've got an API key that I just kind of have hard-coded in here for this open weather map API.
And of course, everybody's taking notes now to steal your. It's okay.
It's okay. I'm going to be deleting this after the show anyway. So what I'm just going to do is I'm going to send this stuff over one line at a time. So I'm sending in the key. I've got this thing called URL base where I'm just, this open weather map api.org/data/2.5/weather. This is just the base URL that I'm going to be building stuff off of. So I've defined this other function here, which is effectively a structured, this is an sprintf or sprintf. This is just a formatted string generation. So this is saying this get full URL function takes in a city, which is of type int, and then it calls sprintf with this format string, which is, there's a string here, question mark, q equals another string, this app ID. So this is like the URL that you have to construct to access the REST API. And so I'm just passing in URL base, the city, which is the parameter here. It can be really any city string. And I'm going to pass in the key, which I defined up here. So I'll just send that over the interactive window, and I've got all these things. Still not doing anything useful here. Now it's going to get fun. So I've defined this new type. So it's this type keyword allows you to define what are just called types in F#. There are lots of different types. There are tons of ways that you can learn about them. I'll show the documentation for that after the show so people can understand that, and we'll put that in the description of the show so people can take a look at that. So I'm defining this thing called a JSON provider. Now this is a whole lot of stuff that's going on here, but a JSON provider is what's known as a specific instance of an F# type provider. Now, F# type provider is a way for accessing data and then manipulating that data in a really, really easy way because it allows you to get IntelliSense for that data.
Okay, so how does that work? Because here you're giving it a URL. So what is the compiler doing here? This sounds like magic.
So you'll notice I have this hard-coded URL here where I've passed in Seattle. So the reason why is because I couldn't find a JSON schema for this open weather map site. Maybe there is one out there, but I couldn't find one. I didn't look very hard, but I couldn't find one. So you can either pass in a URL with a schema, and so then the F# compiler will then download that information. It could be on disk, so it could read it off of disk. It'll download the schema information and generate a set of types that correspond to that schema. So it'll be able to read metadata on the file and that sort of stuff, so that you can then use this once you have loaded a data set to get IntelliSense for data. So what I'm doing here is I'm just passing in this hard-coded string here with Seattle. So what it's going to do, it's going to go download a quick data set for Seattle, and the F# compiler is going to generate So you notice I sent that over to interactive window. So the F# compiler now downloaded that data set and it generated some stuff. And so now.
Okay, so I imagine that you have a bunch of code in JSON provider that does that downloading and exposes.
Yeah, and so internally, the JSON provider code itself, it opens up some streams and it does some stream reading and some JSON parsing and things like that.
Right, but the important part here is that you have some F# code that is running as part of the compilation, basically.
Yeah, it's part of your coding experience. It's a bit more interactive because you don't have to
a bit more, yeah.
So I'm going to be doing this thing called let weather data equal to weather context. So I've taken this context that I've created and I'm going to call .load, and I'm calling .load on that same thing. Now, if I had a URL for a schema, I would just pass that in there. Or if I had a location on disk where this was located, I would just pass that in there. So I'm going to load that here. All right, so it loaded a whole bunch of stuff. That's kind of cool. Now this is where it gets a little interesting. So I just want to show people there's nothing special going on here. This is just some commented out code here. There's nothing special going on here. I haven't created anything to do this, but I'll go weather data dot, what's this, base, clouds, so on. So I happen to know that there's, weather, wind. I happen to know that there's this thing called main, which contains the weather information. And okay, so I could look at the humidity. There's a JSON value. This is sort of it knows that it's JSON, so I could try to extract the JSON value. I could look at the pressure, the temperature. Let's go temp. And then I happen to know that it's defined in Kelvin, so I'm going to subtract 273. Let's do that here. So let's see what the value is. Oh, not 273, 237. 61 degrees Celsius would be quite hot. So this happens to be in Seattle because this is the data set that I've passed into this weather context.load. And okay, 25 degrees Celsius in Seattle. Let's see. Weather in Seattle, Celsius. Oh, come on. Okay, well, it's probably about 25 degrees. So this is kind of cool. I've sort of prototyped this out thing. I got this in this property. So notice I'm highlighting this thing. So it's this property JSON provider, and this .root.main, and then this JSON provider .main.temp, and it knows that it's a decimal type. It was able to grab all of this information. The F# compiler was. I'm not running, I'm not explicitly running this project. It's just figuring stuff out for me. So
you didn't have to generate a proxy or any.
Exactly.
Like that.
This is just part of what you get with F#. And so this is, it's really, you might be thinking, oh gosh, this just has to be so slow. But no, it's not, because this is a compile time artifact, this IntelliSense. Internally, it's using streams and a JSON parser, just like you would do if you had to write that code yourself. So I'm going to now context switch out of that script file, and I'm going to uncomment all of this stuff that I have here. So I'm choosing not to type this out right now for the sake of time. But so I've made it a little bit robust. So I've defined this weather context type, and I have a little comment up here saying this is needed to get the schema information. If there was a schema URL, I'd point it there instead of at this specific Seattle data point here. But so then I've defined a few functions here. So I have this module that I'm calling weather logic. And I have this value key, which is just the API key here. I have this value URL base, which it's the same thing there, and this get URL. It's kind of the same thing that we saw in that script file. But I have a new function here, just convert to Celsius. Given a temperature, I happen to know that the temperature is in Kelvin because I played around with it in the interactive window, and I said, well, I need to subtract 273.15 M in this case, which is the decimal thing because it's a decimal type. So I'm going to get rid of this code really quickly. So I have this function here called letGetMessage, and it takes in S. I've explicitly annotated it as a type string. This is optional. I don't have to do this. There are a couple of cases where type inference needs you to be able to you need to give it a hint as to the type because there might be a case where you need to disambiguate, but those are very, very rare. The vast majority of the time, it's able to figure it all
it's
out.
the first time actually that you've had to explicitly declare a type.
Yeah, it's and so.
But everything that you've shown has been completely type safe nonetheless.
Absolutely.
Because it can infer the types from more places than something like C# would.
Oh yeah, absolutely. Okay, that was what I did. Okay. So I'm just going to have this S. So in this case, we know it's a string. So this is kind of this string thing. When I say it's optional, I mean you can, if you're the type of person who wants to have all of your inputs explicitly parameterized, you can do that. That's actually, so in fact, we actually encourage you to do that if you have some public functions as part of a NuGet package or a library that you intend other people to consume. Because then you can explicitly annotate those types sort of as a form of documentation. So I'm going to take this S input, and I'm going to have this let city data, so that's going to contain all the information. I'm going to go S, and I'll go weather context.load. I can also do an asynchronous load. I'm not going to do that right now because then I would have to define an asynchronous function and know how to call that correctly from C#, and that's a bit more work involved. This is just kind of showing off how to do this. We'll go weather context.load, and gosh, now I'm having a brain fart here. Okay, that was indeed all that I was trying to do here. I've totally messed up this commenting thing here. So at any rate, I've passed it into get URL, which gave me the full URL. S, the string, in this case, it'll be the name of the city. Passed it into get URL, which constructs the full URL, and I passed that into the weather context.load function. Now this is a little bit different from the script file where I had a hard-coded string in there. In this case, it's actually generated as you call it, which is fantastic. So we'll go let temp equal to city data dot, now I have this IntelliSense again, this dot main dot temp, and I'm going to pipe that into convert to Celsius. And so that's just passing it into convert to Celsius, and now temp is a decimal. And so I'm just passing it into this format string that I'm then returning. So this format string, I'm saying it's however many degrees Celsius in, and then S is the city. So I'm going to say it's however many degrees Celsius in the city. So that's fun. We can build that. Build started, build succeeded. This is all cool. Now I'm going to actually use this. So I'm going to go ahead and add a reference. This bot function here, or rather this bot project, I'll just show this. This is part of the Microsoft bot framework that we have, which is still in pre-release, if I'm not mistaken. This is just sort of the template here. It uses ASP.NET Web API in the background. And so in this case, there's this activity and there's this message. And so there's this text. And so I'm creating this message and then I'm creating a reply, but all it says is hello world. That's no fun. I want to get some weather information. So I'm going to go to that project. And I'm going to go ahead and add a reference to the bot logic project that I just created. So now, WeatherBot. Or did I call it DemoBot? I called it WeatherBot. Okay. So I'm using WeatherBot. So this is now just as if I'm using just a class library. It happens to be written in F#, but it's just a class library. So go message equal weather logic. You'll notice that in weather logic, that's the name of the module. I now have access to that. I'll go weather logic dot get message. Okay, so I'll call get message, pass in a string. In this case, it's going to be, I think it's activity.text.
So your F# code appears as static functions?
In this case, yes.
Okay.
And well, because static methods, they're really just functions.
Right.
Yeah. So that's the way that it appears. So I could define an object in F# and then
that was going to be my question.
Yeah, and then define methods on that, and then you would have to instantiate that object and then call the methods on that. But in this case, because it's just a function that I'm doing, I'm choosing not to do that. So it's kind of cool. I got IntelliSense for what I was actually had, and it gives me the information there. So let's go ahead and run this. So if you haven't seen the bot framework before, now you're going to see it. So this just launched an instance of the Web API that's able to talk to what I'm going to pass into the bot framework emulator. So let's go Seattle. and it ran some code. It had to do some initial stuff. Okay, so it's 24.99 degrees in Seattle. So we'll go. Let's see what it's like in Denver. Okay, let's see what's in Paris. It's 30.58 degrees Celsius in Paris. That's a lot hotter than here.
Yeah.
Yeah, aren't you glad that you're here instead of there?
Yeah, depends for what.
Let's see. I'm from San Luis Obispo, so let's see. Oh, it's 17.72 degrees in San Luis Obispo. Yeah, I want to be there.
Yeah.
It's got a lot of nice weather there. So, so just to kind of backtrack here, I've defined a class library in F# really, really easily. I scripted out sort of this initial solution using a NuGet package and sort of playing with the information, getting IntelliSense for data. Just, oh my God, that's really cool.
Yeah.
And then converted that into like a more, actual code, if you will, and a module with an actual function. And then now I'm consuming that as a class library from a C# project using the bot framework. And now I'm just playing around with it. I could type any city you want me to. Well, any city that the Open Weather API happens to have. But yeah.
That was pretty cool.
Yeah.
Are you done?
I could go on. I mean, do you want to talk about recursive types? I could tell you all about how you can really, really easily represent tree-like data structures, which are really hard to get right in C#, and they're dead simple in F#.
Sure, we can talk about that.
Well, I'll just do it very briefly. So that's backed by what's known as the discriminated union type. And the discriminated union, you can basically, so like a binary search tree, for example, it's either empty or there's a node that has a binary search tree on the left and a binary search tree on the right. And so you kind of recursively define it as, this is a node that has a value, and it has a tree on the left, a subtree on the left, and a subtree on the right. But then those subtrees are then defined by the same structure that they are effectively defined in. It's sort of this inherently recursive thing, but you just define that in actually 3 lines of code in F#. And then what's really handy is whenever you use that, you get the same thing that we saw with the optional type, which is you are forced to account for the empty case. And then you are forced to account for the case where there's a node and it has the value in the left subtree and the right subtree. And it leads to some very succinct code, and it makes it very, very easy to sort of work with tree-like structures. And tree-like structures are oftentimes kind of the way that you represent a lot more complicated data that you're working with. But that would be another on.NET show.
Excellent.
But I would just want to show a few other things not related to writing F# code, but being supported. So I use that word supported, and I quite mean it. F# is a supported language by Microsoft. We build tooling, and we have a compiler that we build for it, and it's all on GitHub on the Visual F# repository. And so there's something that I just want to show off here. Pulse here. So we'll go period 1 month, just to show how awesome this. So in 1 month's time, we had 64 pull requests from 14 different authors. Now, only 3 of those people were Microsoft. 11 of these contributors were open source contributors doing some really awesome stuff, like some cleanup, not using this stuff, array.choose with less memory usage, a whole bunch of, in fact, a whole lot of these are from some performance improvements that the community has sort of taken it upon themselves to do. And so we're like, whoa, this is fantastic. Super, super engaged community that really, really, really wants to see everything continue to improve. And we are super proud of this because we have such an engaged and very, very active open source community.
Yeah, that's impressive. And it also means that if I'm a beginner in F#, I am going to find some help. People are friendly, right?
Absolutely.
They're not going to mock you because you don't understand monads.
No, oh God, no. Most of the people in the F# community, I mean, so we all understand why monads are important. We understand, there's an algebra that backs it. There's a mathematical basis for all this stuff. But at the end of the day, you just want to get some stuff done, and you want to get it done in a way that you're guaranteed some more correctness.
Right, exactly.
You want to try something new. You want to have a different way of thinking about things. And so the community says, yes, please come. We will teach you. We have Slack channels for the F# Software Foundation, which is a foundation for the F# language. In our Slack, we have like an F# beginners thing where a lot of people come in and they say, hey, how do I do this? What's up with this? And people just like dive in there and just start engaging and helping people out and saying, oh, well, what this really means is this. And it's really cool. And so then we have a couple of other things. So there's also github.com/F#, which is the F# organization. This is effectively backed by the fsharp.org, the F-sharp organization. There are a couple projects here which are effectively, I guess you could say, they're so blessed by the community and so essential in terms of what the community uses that they just make it part of F-sharp projects. So Fake is a build system where F-sharp is used as a DLL not a DLL. F-sharp is used for a DSL for build orchestration. F-sharp.data, the thing that I showed off here, is there. And we also, on docs.microsoft.com/.net some F-sharp in the table of contents here, you can see there's this F-sharp guide. And we have, if you're new to programming, you could go here. If you're new to F-sharp but you know how to program, you could go here. If you're experienced with F-sharp, check out this stuff. So we have a tour of F-sharp where you can see what some code looks like. We're going to be improving this documentation site so you can run these samples in the browser, which is going to be really helpful. And we have the entire F-sharp language reference on here. So you get like a keyword reference. You're like, oh, what are tuples all about? Well, it turns out there's a really fantastic article written that describes all there is to know about tuples, and so you can really understand things. Asynchronous workflows, how you do asynchronous programming in F-sharp, like all of this stuff is here. And so we have a lot of stuff out there for people to learn, a lot of resources out there for you to get going. We just want you to get going. It's a different way of thinking, writing F-sharp code, and we want you to sort of embrace that trying something new, trying it out, see how you like it, and maybe you'll find a way to fit it into your daily workflow.
Do you have a sample application that you can recommend for people who would like to see maybe an example that goes beyond simple stuff and shows what a real application, a real production application looks like?
Not
putting you on the spot here.
Yeah. So in the F-sharp organization, we have some stuff in there. So like in the fsharp.data project, for example, this isn't integrated with C# in the way so you don't see what it looks like in terms of production application, but this you will see examples of what production F# code looks like. So we'll go in this JSON, this JSON runtime.fs. I mean, we've got some types generated in here. We've got these members where we've this is kind of how some of this stuff can look like. So this is industry strength code with these different attributes, these different ways of dealing with stuff. You notice here we've got all these different types that you can use here. This is what a more involved match expression would look like when you're pattern matching in F#. So I would encourage people, if they want to see what real F# code looks like, go to the F# compiler and components organization. So that's github.com/F# and just click through some of these projects. Because really, in terms of using it in your C# code, it's just a class library, right? So going back to this fsharp.data thing, we have this type IJSON document. This is an interface with these abstract things in here. So you use this interface, like once you using fsharp.data. I mean, in this case, you may not use this specific thing, but you're using a namespace in C#, and then you say, oh well, I'm going to do IJSON document, whatever the variable name, equal to some of the thing you're trying to do here, or in this case, you'd be trying to implement this interface, so you could implement it in this JSON document. You could instantiate that and use it if you needed to. It's really just a matter of, it's .NET code once you are using it in a project-to-project sort of solution, because it compiles down to IL, and so you just get types, members, and stuff like that exposed to you in IntelliSense the same way. I don't know off the top of my head an industry strength example project out there that has class libraries being referenced from C# and Visual Basic and what that all looks like. But I can tell you that this right here, this weatherlogic.getMessage thing, that's basically what code will look like if you're calling a function. And if you're calling an object, it's, this connector client object right here could have just been defined in F# for all we know, because it's just a .NET object, and so you knew it up the same way. And then you have your usings up at the top, and that's just how those namespaces, you just use the namespace that you have up here that you've defined, and that's sort of the way that it all plays together.
Excellent. And of course, we had the news a few weeks ago that Jet.com has been acquired by Walmart.
Yes.
Which goes to show how you can build a multi-billion-dollar business on F# and on Azure.
Yes.
which was really nice.
They hundreds of microservices written in F#, like literally hundreds, all deployed on Azure. Tons of F# code. $3.3 billion. There's value there. And if you look at their blog posts, because they have lots of engineering blog posts, they extol all these different benefits of F#. They talk about the type system. They talk about immutability by default. These are the things that it bought them. There's real value in this stuff, business value. It's not just this fun language where you can do some complex stuff that might be harder to pull off in C#.
It was a very, very central choice in their infrastructure.
Absolutely.
We had Rachel Ruiz from Jet.com a few months ago here on the show. So
awesome.
People who are interested can check this one out.
Yeah.
All right. Well, thanks a lot, Philip.
Yeah.
That was great.
Absolutely.
It's been another episode of On.NET. I kind of expected that this one would be a short one, maybe, but actually, it's been awesome. So thanks everyone. Thanks for tuning in, and we'll be back next week. Next week, if all goes well, we'll have Allende from RavenDB.
Ooh, that would be fun.
That will be interesting.
I'm interested in watching that one.
Oh, yeah. Cool. See you, everyone. Bye-bye.
Bye-bye.